Welcome back everyone. So today is the third lecture for class 12 chemistry, and as we were discussing solution chapter, we'll carry on with the chapter today. Alright, so yesterday, that means in the second lecture, we discussed about types of solutions, and we found out that there are two types of solutions: ideal solutions and non-ideal solutions. When we were discussing about types of solutions, we discussed about types of intermolecular attractive forces between the molecules of solute and solvent. Yeah. Now, we found out that ideal solutions are those which follow Raoult's law over the entire range of concentration. Enthalpy of mixing is 0 for ideal solutions, and volume of mixing is also 0. Today we'll discuss in detail about non-ideal solutions. Okay. Now, non-ideal solutions are those in which the interactive forces between the molecules of solute and solvent are not same. That means A-B interactions are not similar to AA and BB interactions. Okay, are not similar to AA and BB interactions. If they are not similar, it will give rise to two types of solutions. Now, what are the two types of solutions? Let's discuss. The first one, number one, non-ideal solutions. Non-ideal solutions showing positive deviations from Raoult's law. Non-ideal solutions showing positive deviations from Raoult's law. Let's understand what this kind of solutions are. Again, we'll consider a solution which is made up of two components, A and B. This is my solvent and this is my solute. They have their own individual interactions, that is AA and BB. When you mix them, you are expected that the solute and solvent molecules will interact. If the interaction of these molecules, that is A and B molecules, are weaker than AA and BB. Alright, are weaker than AA and BB. In that case, what will happen? The escaping tendency. So, the AB molecules have weak interactive forces. As a result, these molecules will have greater tendency to escape from the solution. In simple terms, their escaping tendency will increase. Okay, their escaping tendency increases. If their escaping tendency increases, vapor pressure of solution will increase. Okay, that means PA is greater than PA naught chi A. Similarly, partial pressure of B will be greater than PB naught into chi B. That means they are violating your Raoult's law. In Raoult's law, we had seen that the partial pressure of PA is equal to PA naught chi A and partial pressure of B is equal to PB naught chi B. Now, since the escaping tendency of the solute and solvent both has increased, then the partial pressure will be more. Done. Let's elaborate this with an example. I hope this much is clear. So we will elaborate this with an example. Okay. What is the example that we will take is a mixture of ethanol and cyclohexane. Ethanol and cyclohexane. Okay. Ethanol C2H5OH. Ethanol molecules are held, they hold each other. That means the molecules of ethanol are held together by hydrogen bonding. So C2H5OH, another ethanol molecule here, another ethanol molecule here, and so on and so forth. Okay, so this continues. When you add cyclohexane to this ethanol, what happens? This cyclohexane, I hope you remember the structure of cyclohexane. Okay, this is an organic compound again. So when you add cyclohexane to this ethanol, these cyclohexane molecules will try to accommodate themselves in this solvent. Okay, will try to accommodate itself in this solvent, and during this process, what it will have to do? It will have to break some of the hydrogen bonds. It will have to break some of the hydrogen bonds and fit in. Okay, and fit in this solution. If it breaks the hydrogen bonds, the ethanol molecules become free. Some of the ethanol molecules become free, and their escaping tendency increases. And also, the cyclohexane molecules also become free, and their escaping tendency also increases. If the escaping tendency increases, vapor pressure will increase. The partial vapor pressure of A and B both will increase because bonds are broken. Alright, so this is what happens in the case of solutions where we have, A and B interactions are weaker. Now, this is the first case. So we have discussed about vapor pressure increasing. Let us see about the energy changes. Now, since bonds are broken, you have to understand that there has been absorption of energy. There has been absorption of energy to break the bonds. In that case, the enthalpy of mixing is positive. That means your process will be endothermic. Bonds are broken by absorption of energy, and if energy is absorbed, delta H, that means enthalpy of mixing, is positive, and your process becomes endothermic. Done? Third condition that we choose for solutions is volume of mixing. Now, it is very well understood that A and B molecules are not holding each other very tightly. Yes or no? There is a loose interaction between A and B molecules. If this so happens, the volume of mixing increases. That is, delta V mixing is also positive. The volume of the solution increases after mixing A and B. So this kind of solutions where there is an increase in pressure from the ideal condition, they are said to show positive deviation from Raoult's norm, because the total pressure of the solution, that is P total is equal to PA plus PB, is always greater than PA naught chi A plus PB naught chi B. Okay, so this kind of solutions are said to show positive deviations from Raoult's law. So let us elaborate this with a graphical representation that we had done yesterday for ideal solution. Alright. So yesterday we have chosen vapor pressure along this axis and mole fraction this axis. Okay, so here chi A, that is mole fraction of component A was 1 and mole fraction of component B was 0. Here mole fraction of component A will be 0 and mole fraction of component B will be 1. Okay, so since here chi A is equal to 1, this will be vapor pressure of pure component A and this will be vapor pressure of pure component B. Now I'll join, since mole fraction is increasing along this axis, this will go in this manner. That is for PB. That is the partial pressure of component B. And this is the partial pressure of component A. So we will join this and that will be here for total vapor pressure. Now I have used dotted lines. This is for the ideal condition. Since the vapor pressure of component A is greater than PA0 into pi A, so I will show the increase in this manner. Okay, so the vapor pressure of component A has increased, the vapor pressure of component B has also increased. Both the vapor pressure has increased, the total vapor pressure of the solution will also increase. That means P is equal to PA plus PB, and this was the solution. This is the ideal condition graph. The dotted ones is for the ideal condition and this is for the positive deviation. So this plot is for solution showing positive deviation from Raoult's law. Okay, I hope it is clear. Now, one important thing that I want to mention here is we have written that enthalpy of mixing is endothermic. Okay, enthalpy of mixing is endothermic. If on mixing cyclohexane to ethanol, the process is endothermic, we must remember that dissolution process will increase with rising temperature. This is in accordance with Le-Chatelain's principle. That means if on mixing the solute with solvent, the solution that we get and the process is endothermic, delta H is equal to positive, and increase in temperature will shift the reaction in the forward direction. This is what we learned last year. So you must remember this. In this case, dissolution process will increase with increase in temperature. Okay. Next slide. Next we will do non-ideal solutions showing negative deviations from Raoult's law. Showing negative deviations from Raoult's law. If you have understood positive deviations, negative deviations will become very easy. In this case, AB interactions will be stronger than AA and BB. Will be stronger than AA and BB. Clear? That means A molecules and B molecules are holding each other very tightly. The interactive forces, interactive molecular interactions are very strong. If this happens, the vapor pressure, the partial vapor pressure of A will be less than PA0 chi A. Similarly, for partial vapor pressure of B will be less than PB0 chi B. And the total, that is PA plus PB, will always be less than PA0 chi A plus PB0 chi B. Alright, so this is about the vapor pressure. Let us elaborate this with an example. I'll choose the example of a mixture of acetone and chloroform. Acetone and chloroform. Now acetone is nothing but propanol. The formula of propanol is CH3, C double bond O, CH3. And chloroform is CHCl, Cl and Cl. Okay, that is CHCl3. When you add chloroform to acetone, hydrogen bonds are formed between the molecules of solvent and solute. Okay, now due to new interactive forces which are stronger than the previous ones, the escaping tendency of both the solvent and solute decreases. If there is a decrease in escaping tendency, vapor pressures will decrease, and those kind of solutions are said to show negative deviations. Okay, so new interactive forces are developed. So I'm done with the first criteria. Second criteria. Now when bonds are formed due to new interactive forces, energy is released. That means my enthalpy of mixing will be negative. That means my process is exothermic. If the process is exothermic, we must remember following Le-Chatelier's principle, dissolution process will decrease with rising temperature. If the process is exothermic, dissolution process, that means the more you increase the temperature, the solubility will decrease. That was the second point. And third is volume of mixing. Okay. Now, A and B molecules are holding each other very tightly. That means the new bonds that they are forming are much stronger than the previous ones. So in that case, the volume of mixing will also become the total volume will also decrease. So enthalpy of mixing becomes negative. Okay. So these are the conditions, or these are the criteria that are shown by solutions which show negative deviation. That means vapor pressure of individual components is less, enthalpy of mixing is negative, volume of mixing is also negative. Last, we'll have to check the graphical representation. Okay. Now, in the similar manner, we'll take vapor pressure here and mole fraction here. Okay, so here chi A equals to 1, chi B equals to 0, chi A equals to 0, chi B equals to 1. This is PA naught, PB naught. Alright. This will go here. So this is PB naught now. And so this is partial pressure A, partial pressure B, and this is the ideal vapor pressure of the solution. Now, since there is a decrease in vapor pressure, I will show that like this. That means the partial pressure of A has decreased, the partial pressure of B has decreased. As a result, the total vapor pressure of the solution will also decrease. So this is our P is equal to PA plus PB. That means the vapor pressure of the solution, and this is for the ideal. So you can see that this solutions where there is a decrease in vapor pressure on mixing the solute and solvent, they are said to be solutions which show negative deviations from Raoult's law. Okay. So we'll stop the discussion about types of solutions here. Alright. So the next topic that we will discuss is azeotropes. Now before we discuss about azeotropes, we have to recall our idea or something that we know about, that is boiling temperature. Okay, because I've written here minimum boiling and maximum boiling. So we need to understand what is boiling temperature. Now, for a liquid, for any liquid, the boiling temperature of that liquid is when the vapor pressure of the liquid becomes equal to the atmospheric pressure. So this is your liquid. You heat the liquid, it develops vapors. Okay? When the vapor pressures of the liquid become equal to the atmospheric pressure, at that point your liquid will start to boil. Clear? Now, we have seen that non-ideal solutions show two types of deviations. Number one, positive deviations, and number two, negative deviations. Okay? When they show positive deviations or solutions which show positive deviations, their vapor pressure was more. Yes, this is what we have drawn and this is what we have learned. Solutions which show positive deviation, their vapor pressures are higher than the ideal conditions or the ideal solutions. If vapor pressure is high, the boiling temperature will be low, because it will be easier for the solution to match with or it will take very less time to match with the atmospheric pressure. So in this case, the boiling temperature will be low. Okay? And for solutions which show negative deviation, their vapor pressure is decreasing or their vapor pressure is less. If vapor pressure is less, boiling point or boiling temperature will increase. Is that understood? So we have understood that for positive deviations, boiling temperature is low, and for negative deviations, boiling temperature or boiling point will be high. Now with this information, we'll study about minimum boiling azeotrophs. Now what is an azeotroph? Azeotrophs are mixtures. Azeotrophs are mixtures of two solutions. Okay? Now azeotrophs are mixtures of two solutions which distill off as a pure component. In class 11, you have studied about distillation. Distillation is a process which is used to separate two miscible liquids. Okay? Is used to separate two miscible liquids which have different boiling points. Okay? You boil the liquid mixture, the one which has lesser boiling point will condense first, and then you are left with the one which is having higher boiling point. Now, we are talking about azeotrophs and minimum boiling mixtures. See here. Suppose you have ethanol and water mixture. Ethanol, the primary source or the main source of ethanol is fermentation. Now, when you obtain ethanol by fermentation of sugars, that particular solution is rich in water. When you distill that solution, when the concentration of ethanol in that mixture is around 95%, the composition of liquid phase and the vapor phase. The composition of liquid phase and the vapor phase becomes same, and it will distill off as if it is a pure liquid. And when this happens, the temperature at which this happens is lower than the boiling point of pure ethanol and also the boiling point of water. Okay? So you are able to obtain only 95% pure ethanol at a temperature which is lower than the boiling point of pure ethanol and that of water. That is why it is known as minimum boiling azeotroph. Even after you continue distillation, you will not be able to get 100% pure ethanol. Okay, so you have to choose other methods. That was about minimum boiling azeotroph. Let's discuss about maximum boiling azeotroph. Now for maximum boiling azeotroph, we have to understand that the vapor pressure has to be low. The vapor pressure has to be low and the boiling temperature will be high. The mixture that I will choose is HCl and water. When HCl and water mixture is distilled, okay, and when the concentration of HCl in the mixture is around 20.2%, the composition of liquid and vapor becomes same, and it will distill off as if it is a pure liquid. But it is not a pure liquid. We must remember that it is a mixture. It contains around 20.2% of HCl. And when this happens, the temperature is higher than the boiling point of HCl as well as the boiling point of water. That is why it is known as maximum boiling azeotrope. Okay, that is why it is known as maximum boiling azeotrope. Now, in the boards or in even in entrance examinations, questions are asked from azeotrope section. They will give you examples of solution. They will give you examples of mixtures. Okay, and they'll ask you that AB molecules in the solution have developed greater intermolecular interactions. Discuss about the type of azeotrope that it will form, whether it will be maximum boiling or minimum boiling. So you'll have to answer accordingly. Clear? Alright, let us continue. And the topic that we are going to discuss now is one of the most important topics of the chapter, that is colligative properties. Let me begin by reading the definition first. What are colligative properties? The properties of the solution which depend only on the number of solute particles but not on the nature of the solute. Okay? The properties of the solution which depend only on the number of solute particles but not on the nature. There are 4 colligative properties: relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. We will discuss about the first colligative property today, that is relative lowering of vapor pressure. Okay? Now, definition of colligative property is extremely important. This is one thing I want to mention before we start. Okay? Now, relative lowering of vapor pressure. To understand relative lowering of vapor pressure, we have to go back to our idea of solution where we studied about solution of solid and liquid. Let us prepare a solution where we have taken A as a solvent, okay, a volatile solvent, and we add B, which is a solute, and it is non-volatile. Okay, this is a non-volatile solute. In that case, the vapor pressure of the solution will be only due to the vapor pressure of the solvent. So that will be PA. Since your solute is not volatile, it will make no contribution to the vapor pressure of the solution. Clear? Now, so we start from here. Vapor pressure of solution is equal to vapor pressure of solvent only. Now, we know that according to Raoult's law, vapor pressure of the solvent, that is PA, is equal to PA naught chi A, where PA naught is the vapor pressure of the pure component A and chi A is the mole fraction of component A. So we can write P is equal to PA is equal to PA naught chi A. Done? Now, since we have some amount of solute into the solution, we must always remember that chi A is less than 1. And the vapor pressure of the solution is also less than the vapor pressure of the pure component PA naught. Okay? So, if this happens, the lowering of vapor pressure, delta P will be vapor pressure of pure component minus vapor pressure of the solution. That is PA, the solvent. Okay, so delta P is equal to PA naught minus PA. We know that PA is equal to PA naught chi A. Let's take PA naught common. So we get PA naught 1 minus chi A. You all know that 1 minus chi A can be written as chi B. Yeah? So we have delta P is equal to PA naught into chi B. Let's bring this down here. So we have delta P by PA naught equals to chi B. We know that delta P is equal to PA naught minus PA divided by PA naught equals to chi B. So this is my relation. Now in this relation, you must remember that PA naught minus PA is the lowering of vapor pressure. PA naught minus PA is the lowering of vapor pressure, and the ratio, that is PA naught minus PA by PA naught, is the relative lowering of vapor pressure. Okay, so PA naught minus PA is the lowering of vapor pressure, and this ratio is the relative lowering of vapor pressure. So what do we find? That the relative lowering of vapor pressure is dependent only on the mole fraction of the solute. It is dependent only on the mole fraction of the solute. Clear? So this is was about lowering of vapor pressure. Now the more amount of solute you add, the more vapor pressure will go on decreasing. Okay? Now with this relation, we will try to derive a relationship to find out the molar mass of the solute. Let's see how. This derivation, this relation is very, very important. Okay? There will be numericals from this section. Let's start. Determination of molar mass of solute. Determination of molar mass of solute. We know that our relation was PA naught minus PA divided by PA naught is equal to chi B. We know that the mole fraction formula is given by number of moles of B by number of moles of A plus number of moles of B. Now, number of moles of solute is given mass by molar mass. Similarly, Na will be, that means for solvent, it will be given mass of the solvent, Wa by Na. Okay? So let's put this value here. So my chi B becomes Wb by Mb divided by Wa Na plus Wb by Mb. Okay? So we will replace this here. So PA naught minus PA divided by PA naught will be Wb by Mb divided by Wa Ma plus Wb by Mb. Wb by Mb. Now, you must remember that for dilute solutions, the number of moles of B is very, very less. It's very, very less, okay? In that case, we can consider that Na plus Mb is approximately equal to Na. That means number of moles of A plus number of moles of B is approximately equal to Na. So I can ignore this entire factor in the denominator. So what does my relationship become? My relationship becomes PA naught minus PA by PA naught is equal to Wb by Mb divided by Wa by Ma only. So let's put this up. PA naught minus PA by PA naught is equal to Wb into Ma divided by Wa into Mb. If I bring the molar mass this side of solute, So it will be written as WB into MA divided by WA into PA naught minus PA divided by PA naught. Okay, so this is the final relation. Using this formula, you have to calculate the molar mass of the solute that will be asked to you in numericals. This numericals we'll do in the next lecture. I'll solve one example for you. Okay, so this derivation, the previous one, please prepare notes on this. I hope you have understood whatever was taught today. So we are left with the rest of the three colligative properties and a topic which is known as abnormal molar mass. Okay, thank you everyone and stay safe.